will not be sufficient for me to complete the portion. I think I have stopped. Did I stop till this? Did we do the loop part was?
We were in the previous slide, I think.
Okay, this one?
Yes, ma'am, this is where we were.
Yes, ma'am, you were where you were telling us about the previous
fine.
one.
I'll start.
Left-hand rule.
Go for the
And the
I'm just
right-hand thumb.
notes. Let me send you the notes for this chapter separately. So just write the running notes, whatever is being shown. Go the loop. Go for the loop. So the loop is.
Ma'am, your voice is breaking up again.
It might be I'm just moving away from my system. A B C D is the loop, correct? The loop, Amperian loop, we have taken as ABCD. Now the question is, you want to find what is the strength of the electric field at point P. So now we'll start with this. Yesterday we have seen when the current is flowing anti-clockwise, so your magnetic field is B vector will be always towards your right. So let me try. Along the loop, along the line segment AB, if I take
Ma'am, your voice is breaking and coming.
Okay, then in that case, I'll wait, boss. I'll connect it to this. Is this fine?
Yes, ma'am, it's better than before.
Okay. Am I audible right now? Boys, am I audible or still there is an issue?
Yes, ma'am.
Okay, fine. Now let me go. Okay, fine. Let me go for an element dl vector. So anyway, magnetic field will also be B vector will also be acting towards the right. So now let me take the element dl vector along the arm BC. So you have dl vector, then your magnetic field is B vector. dl vector along DC, your B vector, right? And in this case, dl vector and B vector. So I want to find what is the total magnetic field enclosed by this loop. So according to Ampere's circuital law, the total magnetic field due to enclosed by the loop. So the total magnetic field.
Ma'am, the magnetic field for AD and BC will become 0, right?
Yes, correct. So that is line integral B dot dl. We have to consider for the entire loop, right? Either you write with this symbol, like the integral symbol with a circle, which means this is for the entire loop. This one I can break this as B dot dl. So from A to B, which means how much amount of magnetic field is almost trapped by this arm AB. That's the first term, right? Then from B to C, B dot dl along the line segment BC, then along C to D, B dot dl, then finally from D to A, B dot dl. Please start writing, boys. Complete this.
Ma'am,
So according to Ampere's
just
circuital
a
law, the
second.
total magnetic field, you're going to find the magnetic field at point P. So line integral B dot dl, this is for the entire loop. So you are breaking it into the magnetic field due to all the other segment, or the magnetic field trapped by each of these segment. So now I need to elaborate. So I can get this as A to B, B dl cos 0, because B vector dot D vector is B dl into cos theta. Here it becomes cos 0 for the first side, AB, DL and B vector are along the same direction. Next, B to C, it will be B DL cos 90. Then for the next one, C to D, it is B DL cos 180 degrees. But still we are going to neglect this because any point along DC is lying external to the solenoid. Boys, if you can remember, the arm DC or the segment DC of the loop is lying outside the solenoid, current carrying solenoid. So the magnetic field can be neglected. Plus line integral D to A B dl cos 90. So now these two terms will become 0. These two terms will take the value 0. But the term which is this term, now that can be neglected because we can say DC, the arm DC of the loop is lying outside the solenoid, or I can write the strength of the magnetic field outside the solenoid is 0. Is 0, or I can neglect. So I can say the strength of the magnetic field, strength of the field outside the solenoid is negligible. Outside the solenoid is negligible. So complete this, boys. B, are you there or switching on your system and somewhere? Are you all literally there, 12B?
Yes, ma'am.
Ma'am, should we draw a solenoid in the diagram?
No, boys. One diagram with the solenoid, the other one just a loop to be drawn separately. Or you can have, 1 second, if you can. This diagram at least. So one should be, right? These two diagrams are important. Sometimes they'll ask you to draw the magnetic field pattern. So this diagram as well as the second one with the loop.
Okay.
So two diagrams are necessary, this and the other one. Complete this, boys. Dheeraj?
Yes, ma'am.
Derek, boys, don't waste.
Yes, ma'am.
Okay, fine. Don't waste your opportunity, boys. This is an opportunity for you all to put yourself in right track and learn. So tomorrow 6:30 I'll start, boys. Please do. Genuinely, if you can't, if you have your coaching classes, fine. Otherwise, I'm going to solve all the numericals possible if I'll go for sample papers also.
Ma'am, you will
6:30
record the
what?
class, right?
6:30 evening.
Ma'am, you will record the class, right?
I'll record the class. But since I'm recording the class, don't run away, boys. If it's genuine, run away.
Ma'am, so there's class tomorrow, like extra class
So
after
yes,
school?
yes, I have to keep,
Okay,
boys,
ma'am.
because I'm not able to complete even the theory part Now, if I keep talking, I think so I'm wasting my time. Finish it off, boys. I've written everything on the chat box. Just if any doubts, just send me a message. That's it. Shall I go for the next one? Shall I go for the next one?
Yes, ma'am.
Now look at this. All these are neglected. So finally you'll get, I think so, I'll start writing. That would be better. Now what is left? So line integral b vector dot dl vector finally comes to a to b dl. So if I take the line segment of the loop AB, say it has a length L. So if because I'm breaking this line segment AB into DL, number of elements, DL, DL, right? So if I'm adding all the DLs, I'll get the length of the loop, where L is the length of the segment AB. So I can write this as line integral B dot DL will be equal to B into L. So this will be equation 1. Okay. Now, according to your Ampere's circuital law, you have that line integral B dot DL. Line integral B dot DL will be equal to mu naught times I into mu naught I is for a single loop. What is mu naught I is for a single loop, right? So now this becomes N into L. What is N? What is N? N is the number of turns per unit length. Number of turns per unit length. Then what is N into L? Now look at this loop A, B, C, D. Now look, this is the entire length L. So the number of turns contained in this loop is N into L. Are you clear, boys? Capital N is total number of turns of the solenoid. Your solenoid will be this way, right, boys? The entire thing is your solenoid. Now you're taking a small part of the small loop ABCD. Now this loop will have few number of turns, and the number of turns enclosed within the loop is N into L. Are you clear, boys? Capital N will be total number of turns. Small n will be the number of turns per unit length of the solenoid. And please be very, very clear. Small n is the number of turns per unit length of the solenoid. The entire solenoid is small n. Capital N is total number of turns of the solenoid. Total number of turns of the solenoid. This we have already initialized. Then what is N into L? N into L is the number of turns of the coil enclosed within the loop. So that you have to be clear. This is number of turns within the loop, within that Amperian loop ABCD. So that you have to be careful. So now when you, okay, now this will be equation 2. So when you are equating 1 and 2, because left hand sides are the same. So when you equate equations 1 and 2, you will be getting B into L is equal to mu naught I N into L. So L and L will get cancelled, or B is equal to mu naught N I. So N into L is the number of turns which happens to be within the loop. But what is small n? Number of turns per unit length of the entire solenoid. Have you completed this? There was no Johan.
Yes.
Okay.
Ma'am?
Yes.
Ma'am, what's small n again?
Okay. If shall I? One second. Complete this. I'll just give an example because I think so here if I'm erasing everything. 1 second, boys. Let me erase this.
Ma'am, small n is the number of coils within the loop, right?
N into L. N into L is the number of turns. Okay, fine. Let me go for this. Suppose this is your entire solenoid, right, boys? So total number of turns, say it is 100, right? The length of the entire solenoid, capital L is the length of the solenoid. Say it is 10 meters, right? The length of the solenoid is 10 meters. Then in 1 meter, how many turns are going to be there? So what is small n? Number of turns in a length of 1 meter. Number of turns per meter. So what is n then? 100 by 10. So n becomes equal to 10. So that is, in a length of 1 meter, there are 10 turns. That is small n. Capital N is the total number of turns of the solenoid. Capital L is the total length of the solenoid. Then in a length of 1 meter, how many turns are going to be there? 10. That is 10 number of turns will be there in a length of 1 meter. Okay. Now I am going for an Amperian loop. Say this is my, right? This is your Amperian loop. Now if this Amperian loop might be the length might be 1 meter or whatever it is. So then it will be very, very less. In that, if this value has to be slightly fine, anyway, let me go for how many meters can I have? Say centimeters. Let me go for centimeter. So centimeter means meters. L will be 0.10 meters. So in this length, within this length, how many turns are enclosed within the loop? That is n into L. So n into L is nothing but the number of turns which are going to be enclosed by the loop. That is what we call it as n into L. So you have to be careful, boys, here. So you have to multiply 10 into 0.10. So literally it's very less number because numbers cannot be in fractions. Since I've given the value this way, you should understand. So how many number of turns will be enclosed by that loop is n into L.
Ma'am, so for only one loop, it's nu naught I in Ampere's
Yes.
circular law.
Yeah, you not?
Ma'am, for one loop is the B dot dl nu naught I?
For this is for the entire loop. 1 second. See, there are different ways of writing. B dot dl, I can write this as for the loop A, B, C, D. So that is for the entire loop. So your aim was to find, boys, what is the strength of the magnetic field at a point P within the core of the solenoid, right? For that, you're constructing an Amperian loop. The Amperian loop is going to pass through the point P and enclose the element. So what will be the magnetic field at point P? For that, you're constructing an Amperian loop and you're going to find how much amount of magnetic field is trapped by this loop.
Okay, ma'am.
That is what is line integral B dot dl. It means how much amount of magnetic field is trapped by this Amperian loop. So that gives you the strength of the field at point P. Fine, boys. I've completed that. If I keep sitting here. Anyway, Nicole, I'll do it later. 1 second. one, it is toroid. Now you should know what is a toroid. Toroid is nothing but if you have your solenoid. What is solenoid? A number of turns of insulated copper wire wound in the form of a cylinder is a solenoid. Now, if I make this solenoid into a join the ends of the solenoid and make into a circular one, so that becomes a toroid, right? Basically, it is a solenoid. Only the geometrical form is going to change, right, boys? And can you see this? You have to be a little bit careful because 5 years ago we had a question in the board paper where they didn't mention whether it was a solenoid or whether it was a toroid. So students have to analyze looking at the description given. If they would have made a mistake in identifying toroid as a solenoid, the entire question would have gone wrong, answer would have gone wrong. So you have to be very clear about what is a toroid, what is a solenoid. Can you see? You have a donut shaped magnetic material, any magnetic material. It can be an alloy. A few alloys are also good in retaining magnetism, or it can be a donut shaped material made up of iron. Iron is basically magnetic in nature. Now over this, you are winding the number of turns of a insulated copper wire, and then when you pass current through this arrangement, now this is going to create a magnetic field. This is called a toroid. Are you clear, boys? I think you would have seen toroids in so many applications, especially in your electric fans, motors, everywhere toroids find an important application. Now, a current toroid is going to create a magnetic field. Now, you're going to find the magnetic field at the core of the toroid. In this diagram, can you see the highlighted green broken lines, boys? Can you see the highlighted green broken lines? Yes or
Yes,
no?
ma'am.
Okay.
Yes, ma'am.
So that is called the core of the toroid, right? Core of the toroid. So you're going to find the strength of the magnetic field at any point in the core of the toroid. Next one, you're going to find the magnetic field at the empty space inside the toroid. Can you see this? At an empty space inside the toroid, you're going to find what is the strength of the magnetic field. Third one, at an external point, somewhere outside the toroid, you're going to find what is the strength of the magnetic field. So there are three different points. One is along the core of the toroid, the empty space inside the toroid, and one is the empty space outside the toroid. Okay.
Ma'am, the empty space inside the toroid is the center.
Yes, it is at the center. Right, boys? 1 second. Did I make you to? Right, boys. A solenoid bent in the form of a closed ring is called a toroid. Please do write. A solenoid bent into a form of closed ring is called a toroid. Let capital N be the number of turns of the toroid. So this will be your basic introductory part. That will be the let us find the strength that will you can skip the last three lines because we'll take each one as your subdivision. Okay, now we'll go for just write a solenoid bent in the form of a closed ring is called a toroid. Let capital N be the number of turns of the toroid. Okay, fine. I don't know. Now look at this. This
Could you
diagram.
back, please?
Okay. Only this statement is enough, boys. Shall I move? I think so. It's getting late.
Yes, ma'am.
Okay. Now look at this diagram, boys. I think so. What I'm let me highlight it. Okay. So look at this diagram. Now in each and every turn of the coil, I'm just holding this, right? If I let me take a single turn of the coil, right? Now, how to find the direction of the magnetic field, right? Can you see the second diagram where you have your right hand thumb rule, right? Boys, can you see the second diagram where you have the right hand thumb rule? Now, your fingers, you bend the fingers in such a way. Look at the current in the coil. You bend your fingers along the direction of the current because the current is flowing in the downward direction in accordance to this. So then, in which direction will be your magnetic field? Your magnetic field is along the direction of the thumb, right? So suppose if I take this entire small turn of the coil, right? So in accordance, where will be your thumb pointing? This is the direction of your thumb pointing. So the thumb points along the direction of the magnetic field. Are you clear how to find the direction of the magnetic field? Is that clear, Nishant, others?
Ma'am, this is not right hand thumb rule, right? There's some other rule.
Right hand thumb rule. See, right hand thumb rule for straight, that is what I have been telling you, boys. Right hand thumb rule for straight conductors carrying current is that your thumb is along the direction of the current. Fingers wrapped will give you the direction of the magnetic field. This is for straight conductors. But for circular loop, can you see the diagram? For the circular loop, it is the other way. The fingers you have to curl or curve in the direction of the current. Your thumb gives you the direction of the magnetic field. It's totally the other way, okay?
Ma'am,
Yes,
so
ma'am.
this is the opposite, ma'am. Like
Yes.
before the thumb was the current and the hands
Yeah,
were the
fingers.
magnetic field. Here
Fingers
this
were
is the
magnetic field.
opposite.
Here now fingers will be, right? Because the current is flowing in a coil. So you have to just curve your fingers along the direction of the current in the coil. You look at the diagram. He is holding a solenoid, right? He's holding a solenoid and his fingers are curved in the direction in which the current is flowing in the coil. So naturally, in which direction the thumb is going to point, that gives the direction of the magnetic field. So now look at this. Here, in the first, the diagram which I have been, let me highlight the diagram. So now look at the first, this diagram which I have highlighted. So for each and every turn, your magnetic field will be tangential. Can you see a loop being drawn? Because I want to find the strength of the magnetic field at some point inside the core of the toroid. This is the core of the toroid. So if I want to find the strength of the magnetic field at a point inside the core of the toroid, I'm drawing an Amperian loop which is passing through the point. Then you can see at each and every point your direction of the magnetic field will be tangential. At each and every point, the direction of the magnetic field is tangential. Boys, are you clear?
Yes, ma'am.
I don't know how far you are getting this. Boys, this is, which is the, this entire part inside the, this is called the core of the toroid, right? So I want to find the strength of the magnetic field, say at a point which is inside the core of the toroid, right? Then what should I do? Was I want to find what is the strength of the magnetic field at a point inside the core of the toroid. For if that is the case,
Ampere loop.
Yes, I have to draw an Amperian loop which is going to pass to the point where I find the center of, where I want to find the strength of the magnetic field. Okay, you have constructed now an Amperian loop. Now what is my next step? I have to break this Amperian loop into a number of element DL. Yes or no, boys? Yes or no?
Yes, ma'am.
Yes, ma'am.
Okay. So all the entire Amperian loop, I'm breaking into a number of elements. I'm just showing the diametrically opposite point. So I'm breaking the entire Amperian loop into a number of elements, dl vector. So your magnetic field is also at every point your magnetic field is tangential, which means dl vector and b vector are parallel to each other at every point. If I put dl over here, your magnetic field is also b vector. So at every point, dl vector and b vector are along the same direction. Then I have to find what is the magnetic field trapped by this entire loop. Okay, this much if you're clear. Now look at this. There is one, what we call it as the dot and This diagram will be tough for you. Okay. Fine. Boys, can you see this diagram? Suppose I have a loop, sorry, a toroid. I'm just drawing only one turn, right, boys? I'm just drawing only one single turn. There are a number of such turns, boys. There are a number of such turns because there are certain things which you should understand. Now, in this case, at this point, this is the current which is flowing to the toroid. At this point, the current is coming out. Because at these points, the current is coming out of the toroid. At these points, the current is entering into the toroid. Yes or no? Look at how the current is flowing. At this point, the current is coming out of the toroid. At this point, the current is entering into the toroid. That is why previously dot and cross, we represented it for current, sorry, magnetic field. Now this is for the current. Yes or no? Look at the direction of the current.
Yes, ma'am.
At this point, the current appears to come out. At this point, the current appears to move inside. So at external point, it appears to come out. Somewhere at the internal point, it appears get inside. So that is the reason all the dot represents current moving out or flowing out. It denotes the current is flowing out. The cross one represents current is flowing into or inwards. Okay. So here it's not the magnetic field, it's the current. So I've constructed an Amperian loop, boys. It's like this. Can you imagine? Because it will be too difficult for you if I'm just complicating with everything. Are you clear, boys?
Yes, ma'am.
Okay, now I have constructed an Amperian loop. I want to find the strength of the magnetic field at some point inside the core. So line integral B dot dl. So that becomes equal to B dl. The angle between them is cos 0. So B comes out, it is dl. So when I add all the dl's, will it not be the Amperian loop, boys? The entire Amperian loop I'm dividing. So yeah, it will be 2 pi r, because let me take the radius of the Amperian loop, where r is the radius of the loop. In this diagram is slightly different. So this is your Amperian loop. R is the radius of the Amperian loop. So that becomes 2 pi r. First, just draw this diagram. For points in the core of the toroid. For points in the core of the toroid. First, if time, because I'm not able to see the time, just let me know when should I stop.
5 more minutes are left.
Okay. For points in the core of the toroid. So just draw only this, boys, because if you want, you can. So I'm just highlighting. This will be your coil. Number of turns of the coil. Okay, I'm just.
Ma'am, that will not be the coil, right? Because the inward arrow is like a little bit inward.
Sorry. Sorry. It has to go in. Sorry, it has to. So this entire thing. So I'm just erasing it. It will be. So the dot one represents, the dot point represents current flowing outward. Current outward. I'm just writing flowing outward. The cross one represents current flowing inward through the coil. Both the cases. Okay. So then we are going to find the magnetic field. So magnetic field at a point P or anything. I have taken it as S, where the magnetic at point S in the core of the toroid. Okay, in the core. So that will be line integral B vector dot dl vector, or I can write line integral B dl cos 0, because the angle between them is B dl cos 0, and since the current is a constant, the field is also very constant. So when I'm adding all the dl's, I'm going to get this as 2 pi r. So mark this as equation 1. Boss, have you completed? At least let me finish this part at least. 12b, I think you.
Ma'am, in the diagram,
People
should we show
listening?
R as the radius
Yes,
of
one, you
the
can
loop?
finish it.
Yes, boys?
Should we show R as the radius of the loop in the
Yeah.
diagrams?
I'll just finish this and then I'll leave. Okay. Ampere's circuital law. In accordance to your Ampere's, yes, it's time up.
No, ma'am. Is R the radius of the Amperian loop or the entire toroid?
No, radius of the Amperian loop. R is the radius of the Amperian loop. So B dot dl is equal to mu naught n into I, your Ampere's circuital law. Because here it is not a single loop, it is the total S.
Then the one in the diagram is wrong, right? If R is the
Right, this R
radius.
should be S, boys. This R
Okay, ma'am.
here, I'm not able to erase this R.
Okay,
This side, this part should not be there. Okay, it's only the radius of the Amperian loop. So this part, 1 second. This part should not be there. Okay. So according to Ampere's circuital law, line integral B vector dot dl vector is equal to mu naught n into I. Why? Because your toroid has n number of turns. Please understand, boys. If it would have been a single loop, it is mu naught into I, like your Ampere law states, but it is n number of turns. Now compare equation 1 and 2. Okay. So n by 2 pi r. So r is the R is the radius of your Amperian loop. 2 pi r is the perimeter of the Amperian loop. So that becomes equal to the length of the loop. Boys, is that correct?
No, n becomes the length of the loop. No, what becomes the length of the loop?
No, 2 pi r, the perimeter becomes the length of the loop, right? 2 pi r is 2 pi.
Ma'am, but then shouldn't it, ma'am? But then, ma'am, it's only that be of one loop, no? Shouldn't there be? There are like multiple loops. So wouldn't that be 2 pi r into n?
No. See, your Amperian loop. The turns of the coil. N is the number of turns of the coil. Because N is the number of turns of the coil. The entire coil has N number of turns. Amperian loop is a single loop. It's a single loop.
Okay. So it'll be 2 pi r will be L.
Now this is your Amperian loop. Amperian loop doesn't have N number of turns, right? This is the radius of the loop. So 2 pi r is the perimeter of this loop, which is equal to the length of the loop, right? So are you right? Then n by L is equal to small n. What is that? The number of turns which is enclosed by the loop. What is it? Small n. It is the number of turns enclosed, or the number of turns per unit length enclosed by the loop. Or the number of turns per unit length.
Ma'am, that is n by L. Ma'am, what is n over here?
Total number of turns. Capital N is total
Yes,
number of
capital
turns.
N.
Yeah.
Ma'am, so is it the same as solenoid?
Same as solenoid. Mu naught Ni. Just check, boys. If it is exceeding your time, please. I'm not able to find the time. If it is exceeding, I think so. It's exceeding.
Yeah, ma'am.
So tomorrow we'll.
It's
Okay, you can leave, boys. Those who have completed can leave. Tomorrow we'll just go
Thank
for
you, ma'am.
the other two parts, and then we'll start with galvanometer. Oops, so I have to finish galvanometer. Then little bit of cyclotron is left. Then we'll finish and start with electromagnetic induction. So 6:30, I'm starting with my classes for numericals, boys. Thank you.
Today?
Tomorrow.